Now let's analyze this example circuit in which we want to find Vx, and Vx is found across this 10 ohm resistor shown here. First we note that now let's start simplifying. We note that the 10 ohm is in series with this 10 ohm, so this is 20 ohms. However, this 20 ohm is in parallel with this 10 ohms in series with this 10 ohm. So this here is really our equivalent of equal to 10 ohms. Since this is in series right here, 10 ohm plus 10 ohm is 20, it's in parallel with this 20, and we know that 20 times 20 over 20 plus 20, to find the equivalent resistance for that, is just equal to 10 ohms, or half. Since these two resistors is just half of the resistance. So this is 10 ohms. Again, we note that then this combination, since this is 10 ohms, then this 10 ohm is in series with this 10 ohms, which is the voltage across Vx. So what I like to do is a voltage divider, since our input is a voltage input. So what we have here is this 20 ohm in parallel with this 20 combination. So what we have here now is our EQ2. We have this 20 ohm in parallel with this 10 ohm plus, I'll call this REQ1, REQ1. Or in other words, 20 in parallel with this 20, which is just equal to 10 ohms. So we can redraw this circuit where we have 15 volts here. So we can put the 20 ohm resistor right here, replace this circuit right here with a single resistor of 10 ohms. We'll call this X again and Y. So the voltage, we'll call this plus minus Vx. Vxy is equal to, using voltage divider, 15 volts. The voltage across Vxy has a 10 ohm resistor, and then we just divide it by the sum of 10 plus 20, which is just 15 times 1/3, is equal to 5 volts. But we note that the voltage Vxy here is 5 volts. This is 20 ohms, and we note that this 10 is also in series with this 10 that we calculated for REQ1. So since this here is 5 volts, half of the voltage drop is across Vx. So Vxy is 5 volts, so Vx, we have 5 volts. This is a 10 ohm. So 10 ohm plus 10 ohm, that's just half of the 5 volts, or 2.5 volts, is the resulting answer for Vx. Okay, here's another example where we're going to illustrate the concept of circuit reduction, in which we want to find the VO shown here using circuit reduction. First we note that R and R is equal to 2R, so we can replace that combination, and we'll convert this Vs in series with this 2R into a current source. So what we have here is a current source in which we can replace it with Vs divided by 2R in parallel with this 2R at point A. Now we've got to replace this R and R combination. We have 2R in parallel with that combination. And then we have this R and 2R right here. VO. And again, I'm going to try to convert this into a voltage divider since I have an input of a voltage and output, but we see here we can reduce now this. 2 R's in parallel becomes a R. Since, again, 2R times 2R, the product of those two resistors divided by the sum, and that's equal to R. Now we can convert the circuit now into the following. So this is now has a voltage source of Vs over 2 in series with R, which is in series with this R, and this is again 2R. So we have a plus minus VO right here. And now we can use voltage divider, which is just simply VO. We have our input voltage of Vs divided by 2, and 2R over R plus 2R, which we just use voltage division. So this is just Vs divided by 2, and this 2R over 4R, which is just 1/2, which is just Vs divided by 4. So that's our final answer associated with this circuit. Once again, let me clarify how we get this current source and convert it into this voltage source. So this is our current source, where we take this current source, Vs times 2R, and we multiply by this resistor combination R, and that leaves a voltage source of Vs divided by 2. And this voltage source is in series with the resistor that we calculate between this 2R parallel combination. So that's our resistor associated with that.